The last one of these conjugate addition reactions that we're going to look at is called the Robinson annulation reaction. And this is also a combination of reactions that you've already learned, kind of like the storkina-amine synthesis. Robinson annulation reaction. So this is a Michael addition that is followed by an aldol reaction, either addition or condensation depending on the temperature. Remember, condensation requires us to have a high temperature. If we have a low temperature, it's just aldol addition reaction, no condensation. So here's what the Michael addition reaction looks like. So we're going to have a molecule. Normally it's going to be a dicarbonyl, but the reactions that you have on sapling are just, at least one of them is just one carbonyl group instead of two, but we'll look at those. I'll show you those examples. And then we are going to react it with a Michael acceptor. So this is going to be something that has conjugated carbon-carbon double bond with a carbon-oxygen double bond, and I'm drawing it on its side for a very specific reason. For this reaction, we're going to use a strong base. You could see hydroxide, you could see LDA, you could see ethoxide, so it really just about anything, and as long as it's strong. And a strong base is going to serve several purposes. It's going to create the initial enolate that we need to do the Michael addition part of the reaction. So let's draw that out. Remember, with the Michael addition part of the reaction, we're going to be forming a bond from the alpha carbon, and if there's two carbonyl groups, we want the alpha carbon that's in the middle. We're going to be forming that bond to what I've drawn as carbon number 1 of the conjugated system. Now you got to be really careful to not lose carbons in this, because it is really easy to lose carbons in this reaction. Remember that the double bond between carbons 1 and 2 goes away. So there's our first product. And then the strong base, the hydroxide or the LDA, whatever we have, is going to attempt to deprotonate at one of the alpha carbons, either 2 or 4. And that enolate, either 2 or 4, is then going to attempt to attack one of the carbonyls to close up and make a 5 or 6 membered ring. So we'll have to think a little bit about which carbon should become the enolate. Should it be 2 or should it be 4? And then which carbonyl group should be attacked. Thankfully, this particular molecule that I picked is symmetrical. So we don't have to focus on the 2 different carbonyl groups because they're the same. It's only one carbonyl group. So all we have to think about is who should become the enolate, carbon 2 or carbon 3. If carbon 2 becomes the enolate, it's going to attack right there, and that's going to make a 1, 2, 3, 4 membered ring, which is no bueno. So that's not what's going to happen. We're going to have carbon 4 become the enolate. Not an option for you, carbon 2. Carbon 4 is going to become the enolate and attack. And do an aldol. This will be like an aldol cyclization reaction. And again, you've got to really, really pay attention to your carbons as you're drawing this product. Don't lose any carbons. Make that bond from carbon 4 to the carbon that, so it used to have a carbon-oxygen double bond. It's going to start out, the initial aldol reaction, it's going to start out like this with an alcohol group on it. And then if you have high heat, so if you have a high temperature, going on, then you are going to get the condensation or the dehydration part of the reaction. And in that, we're going to be taking off the OH group. So we're going to be getting rid of that. And then we're going to be taking a taking a hydrogen off of one of the adjacent carbons. Could be here, could be here, could be here. Those are our adjacent carbons. It actually cannot be up here. Oh, I erased way too much there. It cannot be up here. Oh, I did it again. It cannot be up. Oh my gosh. It cannot be up here because there isn't a hydrogen there to remove. So we're not going to go up there. We don't want it out here because our goal is to try to conjugate. And so we want to put our double bond in this position right here so that we end up conjugating. So let's draw what that's going to look like. Just like that. Beautiful. So let's take a look at sapling. So this is problems 16 and 17 on sapling. And on sapling, you're given this molecule to start, and you're going to be reacting it with, looks like this, with KOH. And it has the delta, which means this is hot. Temperature, hot. So in this reaction, what you're going to do, because this is just a single, it's a monocarbonyl, it's not a dicarbonyl, but it's symmetrical, thank goodness. So this is going to be our enolate, and we're going to initially form a bond between that carbon and the carbon, what I would call carbon number 1 of the Michael acceptor. So it's initially going to look like that. And then you are going to make another enolate, which is going to be out here, and you are going to bring that guy, form a new bond all the way up to here. So when I actually did this on sapling, I'm not even joking. When I did this, I took this molecule right here, started with that, and I literally drew it like that. And sapling didn't even care. It was totally fine with that, except for you've got to make a double bond because you've got high heat. So where's that double bond? It's actually right here. And it looked so gross. And sapling said, cool, you did a really good job. So don't worry about like trying to make this look good. You can make it as gross as you want it. Sapling's going to figure it out. So here's your second one on sapling. You have just a regular like cyclohexanone. And then you have an alkyne / ketone. So that's crazy. With LDA, and this reaction actually tricked me the first time because there's no heat with this one. So that means you don't want to do condensation. So you're going to start with this enolate, and you're going to form a bond right here. And you're not going to get too crazy because we have an alkyne. So you're not going to take that all the way to a single bond. It's going to go to a double bond. So this is what you're going to get to start with. Now you're going to make enolate number 2, and you're going to stretch that bond all the way over like that. And because this is not dehydrating, there's no heat, that's going to make an enol. Again, you can make it ugly. Sapling will figure it out.